We've been talking about thermodynamics, which is the study of energy changes that accompany reactions, whether they be physical or chemical. And we said early on in the chapter, for a reaction to occur, it needed to be both kinetically favorable, that is, it had to occur fast enough, and thermodynamically favorable. And we're going to focus on that thermodynamic favorability aspect in this next section here, as well as the next section. A reaction that occurs without any assistance is said to be thermodynamically favorable. The older nomenclature says the reaction is spontaneous. It occurs without any assistance. So your textbook says spontaneous. The newer textbooks are using the phrase thermodynamically favorable. They are synonymous. I tried to write them in both places in your notes and on your classwork. For example, gases diffuse. That is a thermodynamically favorable process. If somebody sprays perfume in the back of the room, the gas particles will just diffuse from high concentration where you sprayed it to lower concentration that is all around it. You don't have to do anything to facilitate gas diffusion. It just happens. It's thermodynamically favorable. Ice melts at room temperature. I start with a big Tervis cup full of ice with water. I leave it all day, and by the end of the day, the ice has melted. I haven't done anything to it. It is a thermodynamically favorable process. It just occurs. If you have hot soup, we had hot soup the other day for Passover, and we actually celebrated Sunday and Monday because that's what my mommy wanted. So she put the hot soup on the table, but we were watching the Masters because it was really very good. And so our hot soup got cold, and then she yelled at us, but that's okay. But it just cools. You don't have to do anything to it. It's a thermodynamically favorable process. Generally speaking, most exothermic reactions, if you have an exothermic reaction, is delta H negative or positive? Negative, and you need to know that for the quiz, of course. Most exothermic reactions are thermodynamically favorable, but not all, because enthalpy is not the only factor you need to consider as to whether a reaction is thermodynamically favorable. However, in an exothermic reaction, we know delta H is negative. We know it's products minus reactants, so the delta H of the reactants is greater than that of the product. So it is somewhat of a downhill process, and when we do the reaction profiles, you'll understand a little more clearly.
Is the quiz including the lesson that we learned yesterday?
The quiz does not include Hess's law. It does include delta H calculations like number 9 on the classwork. In addition to enthalpy, when considering if a reaction is thermodynamically favorable, you need to consider entropy, a measure of disorder, and temperature. And so we're going to talk a little bit about entropy. Another thing you will see is that some endothermic reactions are thermodynamically favorable, like melting, vaporizing. Those are both endothermic, yet they too are thermodynamically favorable. So when you're considering thermodynamic favorability, you're going to take into account enthalpy, entropy, and temperature. Before we talk about thermodynamic favorability, then, we need to talk a little bit about entropy. Entropy, abbreviated with the capital S, units are a little different here, joules per mole Kelvin. I'll show you where that unit really comes into play in your calculation. Entropy is a measure of disorder. And like enthalpy, entropy is a state function, which means it only depends on the initial and final points. So for example, the same way we talked about enthalpy, where you care about the starting point and the finishing point, the path you take is irrelevant. So you can calculate entropy very similar to the way you calculate enthalpy. Before I show you that, I'm going to show you a little video that truly illustrates that truly illustrates entropy. This is a great little video by Paul Anderson. I especially love his videos. I think they explain things really well. In regard to entropy, this video provides some illustrations that will clearly show you disorder or dispersal. Watch the videos carefully. I think it will really help you. This is an AP Chem video, but I'm only going to show you the initial part, which has basic concepts for honors chemistry. Then it gets far too complicated for the honors level.
Hi, it's Mr. Anderson, and this is Chemistry Essentials, video 57. It's on entropy, which is really the dispersal of matter and energy. So imagine I have a little bit of milk in a glass, and I were to spill it. I will have increased the entropy of this isolated system. And there's an old saying that you shouldn't cry over spilled milk. I totally disagree with this. You should cry over spilled milk. And the reason why is it's an irreversible process. In other words, it's not just going to magically move back into the glass. You increase the entropy, and it's going to take a lot of work to put it back where it was. And so entropy in AP chemistry is not something that you'll have to calculate. You have to understand it qualitatively. In other words, you have to look at a system and figure out what's happening to delta S. And so what is delta S? That's simply the change in entropy over time. Now what does this little degree symbol stand for? That means that we're measuring it at standard temperature and pressure.
Now I disagree with that last piece. You are measuring it under standard conditions, 1 atmosphere of pressure, 25 degrees Celsius.
And so if we were to look at a system, we should be able to make predictions about what's happening to our delta S. And that's what I hope you can do at the end of this. And so if we define it, it's simply dispersal. Dispersal of matter and dispersal of energy. So what are some examples of that? Let's say we're to make some phase change. If we were to go from a solid to a liquid to a gas, what would we be doing? We'd be dispersing or moving that matter away from its center point. And so we'd be increasing the entropy. In other words, our delta S would be a positive value. We can make that matter disperse over time. We also could do that by stoichiometry. In other words, if I look at the moles before a chemical reaction and the moles after, if I have more moles after the reaction, I've increased the entropy. And also, if we take a gas and we increase its volume, we're moving those molecules apart, and so we're increasing entropy, or delta S is going to be a positive value. Now let's say we look at energy. How can we disperse energy? Well, by increasing temperature. We increase temperature of gas, according to the kinetic molecular theory, we're spreading that energy out and we're increasing entropy. Now entropy is a term that people really struggle with, and so I wanted to start with a good example. And so I've got two videos.
You've got to
here.
watch.
The same exact video. It's just that one of them is played forward and the other is played backward. And so your goal is to figure out which one is forward. So let me start playing that. It's just going to loop over
Which
and over
one?
and over again. And so your goal is to figure out which one is forward. So you decided, yeah. The right answer is A. But that was kind of hard. Let's look at another one. I've got a little pendulum here, and let me play this video again. It's the same video clip. It's just that one of them is played forward, and the other is the same clip. It's just played backward.
It's how you read, left to
Figured out
right.
which one is forward? There's some clues in here, but the right answer is B. Let's look at the next one. It should be a little easier now. So if we look at the next one, I'm going to play this again. So again, same video. One's forward, one is backward. Hopefully you figured
B,
this
you
out.
knock it down.
The right answer is
Can't
B.
build
It's
like
being played
that.
forward, and A seems somewhat magical. It's being played in reverse.
How about this
Let's look
one?
at the milk. So if we look at the milk right here, which one is being played forward? Okay, let's figure this out. A is being
Hey, you don't, you guys
So
are
why
being
would I do that?
goofballs.
Well, what we're looking at here are irreversible processes. In other words, if we play it in this direction, it's irreversible. In other words, it's impossible for it to occur in the reverse. Now, it's not totally impossible. That could occur, but it's statistically improbable that it's going to move in the other direction. And so that direction is really important when we start to talk about entropy. Because what happens during an irreversible process is that we're increasing the entropy or the dispersal of that system.
So this is the one time that disorder is a good thing. Natural processes favor disorder. Think about your room. It was very well put together on Sunday. And today's Wednesday. If it's anything like my daughter's room, it looks like a tornado went through. Okay? Natural processes favor disorder. Disorder is one key factor in determining thermodynamic favorability.
And it just doesn't move back, and that'll become really important as we talk about the next few videos.
And that's as far as just wanted you really to see those images so that you could see entropy in action. As I said, entropy is abbreviated with an S. The units are joules per mole Kelvin. If you want to watch the video again, the link is here. It's a measure of disorder, and as I said already, it's a state function, which means the same way that you calculate delta H doing products minus reactants, you can calculate delta S as well. The only difference is if you were to calculate the change in entropy, instead of using this first column as we did the other day, you would use this column here. But you would do it the same way with the sum of the entropies of the products, taking into account the stoichiometric coefficients, minus the sum of the entropies of the reactants, taking their coefficients into account. The other thing of interest is that whereas elements in their standard state have delta H's of formation of 0, their entropies are not 0. I'm not going to ask you to calculate that at this level. If you want to give that example a try a little later on, I'd be happy to provide you with the answer. At the beginning of the class, and I know some of you have slid in a little bit late, I did film so that you wouldn't miss anything, and you probably only missed about 7 minutes. And I will post your lesson as well as the other class's lesson, which is already posted. But we said in order for a reaction to occur, it has to be both kinetically and thermodynamically favorable. There are 3 factors when you consider whether a reaction is thermodynamically favorable. That is, will it occur without assistance? Enthalpy, which we talked about the other day. You know how to calculate the change in enthalpy 2 ways. Entropy, which you just saw, a measure of disorder, and temperature. Before we get into thermodynamic favorability and calculations therein, I want to talk a little bit more about determining entropy, that is the system moving toward order or disorder, simply by looking at a chemical reaction. Reactions that are thermodynamically favorable tend to show an increase in entropy, tend to show disorder. Disorder in a system has a positive delta S, and that's what we're going to look at here. And I'd like to diagram this out for you because it sometimes causes some confusion. So let's take a look at some abbreviations so that you can keep track of all this, and then we're going to add one piece to it at the end. We know that enthalpy is a measure of the heat constant, of the heat content of the system at constant pressure, abbreviated with an H. When the change in enthalpy is negative, that means that the reaction's exothermic. Heat is being released by the system to the surroundings. When the delta H of the reaction is positive, we say that the reaction is endothermic. The system is absorbing heat from the surroundings. That you should be comfortable with. In regard to entropy now, entropy abbreviated with an S also can be negative or positive if you consider the change in entropy. When the change in entropy is negative, the system moves toward order. When the change in entropy is positive, the system's moving toward disorder, and I'll give you some examples of how you can recognize that. Something else that we've looked at this year are phase transitions. For example, solid can be converted to liquid through the process known as melting. Liquid can be converted to gas through the process known as vaporization. Or you could go solid to gas directly by sublimation. When you go in this direction, the delta H for the reaction is positive. It is endothermic.
So from solid to gas.
From solid to liquid, from liquid to gas, or from solid to gas directly, they're all endothermic processes. So anything along this branch here. And it's easy to remember because 99.9% of the time, men will melt your heart. Melting is endothermic. Anything along this branch, endothermic. Another thing to consider here is along this top branch here from solid to liquid or liquid to gas or solid to gas directly, delta S is positive. You're getting increasing disorder. You have seen at the molecular level solids, liquids, and gases. I'll flip back to the screen in a sec. For example, water as a solid. The molecules vibrate in a fixed position. Solids are very orderly. Liquids, the molecules move. They flow. Less orderly. And then finally, gas molecules bebopping all the way around, far more disorder. So as you go from solid to liquid and liquid to gas, you get more and more disorderly. On the flip side of this, if you go in the reverse direction here from gas to liquid, you are condensing, or liquid to solid, you are freezing. If you go from gas to liquid or liquid to solid or gas to solid directly, delta H is negative. The reaction is exothermic. Heat is released. And delta S here is negative because the system is getting more and more ordered. A solid is more orderly than a liquid's more orderly than a gas. And in regard to entropy, just remember, no. Can I stay out till 3 in the morning? No. Negative order. Okay? So that's for entropy. Enthalpy, negative is exo, positive endo. Try and keep those separate. That sometimes does cause some confusion. illustrated in C are processes that show positive entropy, therefore illustrating disorder. Entropy is a little bit of a backward concept. Don't confuse it. So as I said, solid to liquid or liquid to gas, for example, sublimation of iodine, disorder, positive delta S. Liquid to vapor, the vaporization of bromine, positive entropy. When you dissolve a solute in a solvent, for example, let's say that you dissolve solid sodium chloride in water, you make an aqueous solution, the sodium ion and the chloride ion now move freely. The solution has greater entropy than what you started with. Disorder. When you heat a system that has increased the temperature, the particles will move faster. Greater disorder. Decomposition reactions. For example, if you decompose calcium carbonate to calcium oxide and carbon dioxide, initially you have 1 mole of solid. In the products, you've got a solid, but you also have a very disordered gas. And as a result, the entropy increases. Similarly, you can have 2 moles of carbon in the graphite state, a solid. It can react with a gas, but all you generate here are gases. So when you go from solid to liquid or liquid to gas, from reactants to products, you're increasing disorder. The one that I think is the trickiest is number 6. It says in a reaction in which there are gases only, or the number of solids or liquids don't change, an increase in the number of net moles of gas from reactants to products illustrates disorder. I like to think of it this way. On the reactant side, I have 2 moles of gas. On the product side, adding the coefficients, I have 1 plus 3 is 4 moles of gas. Let's say you get a babysitting job. Let's say you're either babysitting 2 6-month-olds or 4 6-month-olds. That sounds terrible. What's easier, babysitting 2 or 4? 2 for sure, because they're all going to cry at the same time. They all need to be changed. They all need to be fed. They all need to be bathed. And if you babysit 4 babies for a night, I hope you got a really good wage, because you will be beyond exhausted, because they won't all sleep at the same time. So 2 is more orderly than 4, and we're just comparing gases now. You have to compare apples and apples, okay? Even if you have like 2 solids on the, let's say you had 4 solids on the left and 3 gases on the right, it's not the coefficient there that's important, because once you generate gases, it'll be more disorderly. So we're comparing the same state of matter gases. And in this one, with the increased number of moles of gaseous product compared to gaseous reactant, entropy increases. I know there were a few questions, and I don't know who was first. I'll just start down the line.
What if you had, say, gases and, like, a gas and a solid, and then you create a gas and a solid? Can you still compare them?
If the stoichiometric coefficients don't change, it'll be too close to call just by inspection, and you'd have to go to the videotape. You'd have to calculate it, and I'll show you one of those. That's a great question.
It's like part of the reason why you wouldn't be able to compare like a gas to a solid all the time is like comparable to like babysitting like 4 2-year-olds. Like you could really compare it to babysitting 2 6-month-olds, because you're not really sure.
Yeah, and that's a really good point, because when I introduced it to the other class, they said, you know, well, what do you want to do, babysit 2 kids or 4 kids? And a lot of the students said 4 kids, because they'll play together and entertain each other. So that's why I was trying to compare apples and apples with just 6-month-olds. Yeah, if you're babysitting 2 6-month-olds versus, let's say, 1 baby and 3 12-year-olds who are all going to sit and do what they're told, then yeah, it's probably easier. So yeah, apples and apples, but good point as well. All right, so let's walk through these examples here. And let's make sure that we understand how to interpret entropy from the chemical reaction alone. Looking at the first one, I see I have all gases. So now what am I going to look at? The stoichiometric coefficients. How many moles of gaseous reactant do I have? 2 plus 1 is? 3. How many moles of gaseous product do I have? 2. So we're going from 3 moles of gas to 2 moles of gas. Are we getting more ordered or disordered? Ordered. And delta S here is? Negative. Be very careful there. It's a backward concept. Remember, no, 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 no. Negative order, negative order, negative order. We've got gaseous iodine to solid iodine. That would be? That's order as well, because you're going from gas, disorderly, to solid, orderly. So that would be negative as well. We've got water in the liquid state to water in the gaseous state. That's going to be disorder. And delta S will be positive. We've got 2 moles of nitrogen dioxide going to 1 mole of dinitrogen tetroxide. The state of matter is the same. So we're going to be becoming more ordered because you decrease the number of moles of gas from reactant to product.
So it doesn't matter what gas it is?
Well, it does a little bit, and it can be a little more complicated. If you're comparing the entropy of this substance with the entropy of this substance, the more atoms you have in that molecule, the more disordered it's going to be, but that's too much for the honors level.
Because wouldn't those have the same entropy?
Actually, no. Let me see if I have them both here.
If you were to distribute the coefficient.
Nah, it doesn't quite work like that. It's not that much of a math problem. Let me see if I have those two here. We could calculate it, but I won't ask you to do that. It won't be that that close. If you compare the entropy of these two, this one has more order than this one. Actually, that's not true. More disorder. That's odd. Oh, I'm looking at the wrong one. Duh. Okay, here it is. So that's as we expected. So dinitrogen tetroxide, because I didn't go up here. So we're looking at this last column here. I'm going to highlight these so we don't get confused as I just did. And we're looking specifically at this column here. And you can see that the dinitrogen tetroxide has more disorder, and that's because it's got 2 nitrogens and 4 oxygen making one molecule where the other has a 1 to 2. So it's a little tricky, but we're just going to keep it simple here. But a good question nonetheless. All right, this last one, the kids told me that what you have in your notes is not what I have here. They said that you have aqueous here?
Yep.
Okay, so if you had aqueous here, then you're getting more ordered because you're going from 2 aqueous substances. Aqueous is disordered like gases. So you're going from 2 aqueous substances to 1 solid and 1 aqueous. So that's, you're generating solids, so that would be order. Had the problem said this, that would be one of those. This whole reaction just looks bad. This is a typo here. This should be NO3. Oops. Hang on one sec. That should be sodium nitrate. Had this been a solid, it really would be too close to call. You couldn't make the call there. You would need values. So we'll leave this aqueous, probably be easier for you, but this should be sodium nitrate. I don't know what happened in that equation. It looks like it got messed up. Yes, Robin.
Is order always negative and disorder always positive?
Yes. So entropy can be predicted from a chemical reaction alone. Entropy is a measure of disorder in the system, and it will be used to determine thermodynamic favorability. So this first lesson just is on introducing entropy and making sure that you understand that entropy, enthalpy, and temperature will be used to determine thermodynamic favorability, and we'll cover thermodynamic favorability in the next lesson.